All right, recording started. Welcome, everybody. This is now week 4 of the collage course. Yeah, we've been talking about coronal heating. We've been talking about some of the nuts and bolts of coronal heating in the past few weeks. You know, if you know how much energy is going in, what does it actually do? And you're also sort of in parallel working on that with the hands-on Jupyter Notebook exercise. Please let me know if you have any questions about that. There's now a hands-on exercise channel on the Slack that you can join and discuss any options. There was a small typo I found that I posted a correction, not in the code, but in the markdown sort of instructions. But that's on the Slack. So now I'd like to delve into a little bit more detail about some of the actual processes. So, oh, I am a little loud. Okay, maybe I should just stand back a little bit. I don't know quite how to change my mic my mic volume from Zoom, but is going back a bit helping a little bit volume-wise? I don't know. I guess
volume is all right. It sounds like your mic might be just overdriven a little bit. It's reaching us not too loud, but it's like clipping a smidge. But this is not something that needs to be solved now if it's not.
Yeah, no, thanks. I wish I knew how to adjust some of these things. I wish there was like a little levels piece of Zoom where I could actually see, whether it's clipping or not. But all right, well, thank you. I will see if there's any ways to tweak that for next week. So this week I'd like to talk about waves and turbulence as one method of coronal heating, and next week we'll talk about reconnection and nanoflares as another. And yeah, after that we'll start to move on to the solar wind and more sort of space weathery type things. I don't quite know about how to change some of these things right on the fly. Hopefully it's not too terrible. All right. So I'd like to talk about waves and turbulence, and hopefully as a corrective to the past couple of weeks of very sort of theory-heavy slides, I want to start with observations and spend a good amount of time on them, summarizing what we see, because what we see actually influences what theorists do in a big way, really, in solar physics. But then I can talk a little bit more about the actual sort of types of fluctuations that we think are there. How are the waves generated? How do they evolve up into the corona? And then eventually, how are they dissipated? Because it's the transition from the energy being carried by the waves to being released by the waves and turned into heat that actually provides the coronal heating from them. And then if I have time at the end, a little bit about turbulence. I did want to define terms in a little bit because, again, observers and theorists have different ways of talking about things. Neither one is right or wrong, but it's good to know the distinctions sometimes. Waves versus turbulence are sometimes defined observationally, just on the basis of what we see. Right, a wave is an oscillation, sort of with either one dominant, period or one dominant frequency. Or maybe just one single pulse that just propagates through. You've heard of a shock wave, or the word wave is often used for that as well. Turbulence just means fluctuations that are anything but that, essentially. Something that's more random or chaotic or stochastic. And sometimes astronomers use turbulence to talk about fluctuations happening on an unresolved spatial or time scale. You might have heard of microturbulence or macroturbulence in spectroscopy. But theorists are different. Theorists talk about waves as these small amplitude solutions to equations that propagate as sinusoids through a system and carry energy through a system or carry information through a system. And turbulence is essentially a superposition of a lot of those little fluctuations, not necessarily wave-like fluctuations, but where essentially you have random oscillations on different scales. And it's rather than propagating energy from one place to another place, a turbulence represents a cascade of energy where the energy is being transported from one set of scales to another set of scales. And the dominant type of cascade in fluid dynamics and in MHD is a cascade from large scales to small scales. And that's sort of just as significant a type of transport as a transport from one place to another, or from the past to the future, I guess. So it's just another way of thinking about it. So yeah, I just wanted to set out some definitions so that we're not talking past one another eventually. But yeah, observations. There's a lot of different types of fluctuations that we can see on the sun. I wanted to start with the photosphere because there's a lot of different things happening sort of simultaneously on the photosphere. This picture on the left represents snapshots from a movie. I don't know how well resolved it is seeing through Zoom. But yeah, there's all sorts of different things going on. And in the last couple of years, people have applied sort of big data Fourier filtering type techniques to try to separate out the different types of fluctuations from one another. So it turns out that in the case of the solar photosphere, you can separate out these fluctuations into the granules and the so-called P modes or pressure mode acoustic waves that are coming up through the interior and then bouncing back down into the interior. And they have very different time and space scales, which makes it a straightforward matter to separate them. But yeah, and I just wanted to talk a little bit more about both of those. But yeah, it's nice to see them in a data analysis sense being able to be separated. The P modes represent acoustic waves, pressure modes, flowing through the solar interior. Rachel McClure was here at CU a few years ago. These waves are flowing through the solar interior. They bounce around, they flow through and then they essentially bounce, the surface is sort of a resonant surface where they bounce back down. And the entire spherical sun sort of represents this resonant cavity. It's very much a three-dimensional extension of other types of resonant systems, like there's the one-dimensional string fixed at two ends and it oscillates only in certain frequencies. There's the circular drum head that only oscillates in certain modes, and this is the three-dimensional version of that. And these precise frequencies, due to the discreteness of the spherical sun, measuring them gives us a lot of information about the properties interior of the sun. This is helioseismology. We have very, very precise measurements of tens of thousands of frequencies that you can plot in various ways. And yeah, it gives us the depth and latitude dependence of a lot of solar interior quantities. I wanted to play this audio down at the bottom. There's a YouTube link. You can click on that yourself in the slides once you get there. Maybe I'll put it in the YouTube description. For a sonification of the helioseismic waves, which is kind of a neat, eerie type sounds that you can hear as it sweeps across these different frequencies, and of course altered to be audible by humans, but it's kind of neat to listen to. The other types of waves that you can measure at the photosphere, or other types of fluctuations, are the granules, which we've talked about. These the cells that represent the tops of the convection cells themselves aren't waves, but there are waves that are sort of being facilitated by them. In this movie of granulation, you can see these little bright points in the dark lanes in between the granules. Those represent vertical magnetic field lines or bundles or flux tubes. And as the granules come and go, the positions of the flux tubes move around. They get jostled back and forth. There's all sorts of other variability that they can have. And there's sort of a little cottage industry in terms of interpreting the horizontal random walk motions of these bright points, which you can trace over time. And you can convert the positions to velocities and essentially, take the Fourier transform of the time sequence of the velocities of these bright points and get a power spectrum of kinetic energy fluctuations as a function of the frequency that can sort of act as a lower boundary condition for any kind of waves that propagate up these these magnetic flux tubes into the corona and even into the solar wind. So yeah, there's a lot that can be done with these. If we move to observations of the corona itself, there are other types of waves that you can see. Many of them you can see on the solar disk in coronal images. The most obvious ones are these things that can happen in the wake of large solar flares. Right, you see on the lower left there this running difference image of this sort of circular tsunami type wave that comes out from the position of a flare, and those can sort of go over the whole surface of the sun, over 180 degrees of angle from that position of the flare. And as those things pass by, things like coronal loops, they can set them going. They can essentially give them a push, and you can watch the loop oscillate back and forth. And there's some sort of data analysis of one of those moving loops here, and you can see it oscillate back and forth and slowly damp down over a few oscillations. And the properties of those oscillations, the frequencies, the amplitudes, the damping times, all can be used to help infer some of the properties of the magnetic field in the corona, which otherwise are very hard to measure on their own. So there's this whole other subfield of coronal seismology. It's not helioseismology, but it's coronal seismology to try to measure magnetic fields from these coronal oscillations. What else? Well, as you move up into the outer parts of the corona, you can start looking above the solar limb. And I tend to think that it's sort of easier in some ways to interpret what you're seeing, because you're not looking at things in projection on a very sort of messy solar disk. You're seeing just sort of relatively small numbers of things off to the side. And there's all sorts of different types of measurements that you can make. There are intensity oscillations, where you see brightenings and dimmings that are propagating away from the sun. And those can tell you about density fluctuations moving away from the sun. This on the right is a cartoon that's illustrating some of these things, trying to illustrate them all at once. You can see features that are sort of swaying back and forth above the surface. I'll show an example of that in a second, and that can be used to get velocities in the plane of sky. POS means the plane of the sky here, the image plane. On the other hand, if you have spectroscopy, you can look at red shifts and blue shifts of features, and if they're coming at you and moving away from you, you can see velocity fluctuations in the direction that's along the line of sight, which is perpendicular to the plane of sky. So in theory, you can get sort of the full velocity vector of fluctuations above the limb. Sometimes the signals get to be very faint as you go up above the limb, and you have to integrate. You have basically open your detector and integrate for a long amount of time, 10 minutes, a half an hour, something like that. And that's usually longer than the period of the wave that you're trying to track. So really what you end up seeing is an RMS average of these Doppler fluctuations that gives you an extra broadening to the line. But that's also a good way of measuring these velocity fluctuations, essentially wave amplitudes of various kinds of waves. There's also the field of radio sounding or radio scintillations, because if you observe a radio source that happens to be passing, say, behind the corona, whether it's a spacecraft or a radio galaxy or something, and the corona, and its radio waves are passing through the corona, its fluctuations in the refractive index of those radio waves can give you information about fluctuations in density, magnetic field, sometimes velocity as a byproduct. And you can, again, learn about waves propagating through the solar corona that way. And yeah, there have been some detections of certain types of waves. I'll talk more about the types in a few minutes. But yeah, no, there's a lot that can be done this way. Let me just show a few sort of picture examples, right? Up at the top, you can see these swaying features where you can, as they sway back and forth, you can measure the velocities within the plane of the sky. You can measure intensity fluctuations as a function of height above the limb. That's these 4 panels to the right here, and it's basically height versus time. So the fact that you see an inclined structure means you see bright and dark features that are oscillating and moving upwards as you go in time. That gives you, say density fluctuations, say sound waves that are propagating up from the corona. Spectroscopy gives you a lot of information. The COMP instrument that's been developed at HAO in Boulder here has been very successful at looking at time-varying Doppler shifts, and you can see these red and blue shifts propagating sort of along the magnetic field. You can almost sort of trace out the magnetic field by looking at these oscillating features going up and down. And yeah, you can measure waves that way. Or again, if you go up higher in the corona, you still have to integrate for times much longer than a wave period, and you can measure these things as non-thermal warming. And there's a whole art to trying to figure out how much of the width of the spectral line is due to temperature and how much is due to waves. But there are ways of disentangling all that too. What else? Oh yeah, and I just to complete the story of measuring waves all the way out into the solar wind. We can send spacecraft out there and just at the point of the spacecraft, measure the magnetic field, measure the density, measure the velocity. And you have a time series, and then you take the Fourier transform of the time series, and you can get a lot of information about waves and turbulent fluctuations. So this is a fascinating piece of data measured at 1 AU that covers 8 orders of magnitude of frequency as measured in the frame of the spacecraft. And the fact that there are these continuous power law distributions of energy, this specifically for magnetic field energy, tells us a lot about the oscillations and the turbulence. We'll talk a little bit more about that later. But I wanted to show you all these pieces because then it's possible to look at the amplitudes under these curves and assemble them all together to try to get a global picture for how the fluctuations evolve, say, from the surface of the sun all the way out into the solar wind. So this is this is sort of a potpourri of different sources of information, and it's plotted as a function of height above the solar photosphere in units of the solar radius. So it's small little things up into the chromosphere, then the low corona, and then the solar wind, and then the heliosphere. The orbit of the Earth is at 215 or so here. But you have the bright points in the photosphere that are being jostled back and forth with a total power of just a few kilometers per second. You've got the swaying spicules from Hinode. You've got the non-thermal widths of spectral lines that can be measured from different spacecraft. And then there's a gap. Then there's all the in situ detections. Helios and Ulysses spanned a large span of radii in the 70s and 80s and 90s. The Parker Solar Probe is now inching its way in and is probably gathering data around 10 to 20 solar radii pretty soon for its next perihelion. So yeah, it's filling in a lot of this gap. Yeah, and there are trends, and we'll talk more about why does the actual velocity amplitude of, say, alphanic fluctuations, why does it increase as you go up in radius, then why does it decrease? So there's a lot of interesting physics, and we'll come back to that. Yeah, there's that gap in between. There's so much we want to do with that gap. So yeah, so a little bit more about the physics. I've talked a lot about different types of waves. I've talked about alphane waves that are these transverse kinks in the magnetic field that can propagate along the field, much like plucking a guitar string and watching the transverse fluctuation go along the guitar string. And it depends on there being a magnetic field. And if you want to write the energy density that's carried by these fluctuations, it's sort of made up of 2 pieces. There's the transverse velocity fluctuation, sort of a kinetic energy component that takes the form of these transverse motions. And then there's the actual kinks in the magnetic field itself that are departures from this sort of horizontal magnetic field as I'm showing it here. The question about difference between a kink mode and a transverse mode, I will talk more about that soon. Whoops, sorry about that. Yeah, so there are, so that's an alphane mode. The other sort of extreme is the acoustic or sound wave, right? It's the kind of wave that you're hearing right now from my voice, no matter how it's coming through, hopefully. where it's with this sort of slinky analogy, it's sort of a perturbation in velocity along the direction of propagation of the wave. So there's a kinetic energy component there. But then as this motion along the direction of the wave runs into the material in front of it and escapes from the material behind it, there are density compressions and rarefactions that propagate through also, and they're proportional to the pressure and temperature variations also. But we often sort of just talk about them in terms of density fluctuations. And again, for both the alphane and the acoustic, these two pieces are often roughly in equal partition with one another. In other words, these two components are roughly each carrying 50% of the total amount of energy through the system. Yeah, and of course, this slinky analogy isn't telling the whole story because it's showing them the two types of waves propagating at the same speed, but we know alphane waves propagate at the alphane speed, acoustic waves propagate at the sound speed, which is proportional to the square root of the temperature. And in a generic plasma, you can have different values of these things, right? In the solar corona, the alphane speed is thousands of kilometers per second. The sound speed is only about 100 kilometers per second. So what we have here is a small value of the plasma beta ratio. This ratio of sound speeds is roughly the same as the ratio of the gas pressure to the magnetic pressure. So when this is small, the magnetic field is in charge. When this thing is large, the gas pressure is in charge, and the magnetic field just sort of follows along passively. Yeah, there's all sorts of other things that can be talked about here, right? In MHD, there's really three modes: the alphane and the fast and the slow magnetosonic waves, which are modifications of the acoustic waves when there's a magnetic field. They don't always have to propagate at either the alphane or the sound speed. They can propagate at essentially any speed in between 0 and the square root of the sum of the squares of the two. And in general, they can carry different combinations of these types of amplitude fluctuations, right? There are sort of 4 of them on display up here, and the one that I didn't show was the parallel variations in the magnetic field along the direction of propagation. But yeah, in general, MHD waves can be sort of any combination, have various distributions. I have a plot of a pie chart of different types of how the total energy is broken up into these different pieces for different types of fast and slow modes. I could share that if anybody wants it. Now, unfortunately, that's not even the whole story. If you put aside the magnetic field, there are other types of flavors of waves that can happen in the corona, and that's because the magnetic field and the gas pressure gradient aren't the only forces in the system. Gravity is sometimes an important force in the corona. You're sitting right above the sun, and you'll often hear solar physicists talking about P modes and G modes, pressure modes and gravity modes, not just below the surface in terms of helioseismology, but above the surface as well. In general, it's really magneto-acoustic gravity waves where they all sort of play with each other, but that's a complication that I don't think we need to go into. If we just look at the gravitational stratification, you can get a feel for what that does. There's this standard plot that's similar to the helioseismology plot of frequency versus the horizontal wave number. I think these are actual helioseismic modes that have been measured. And at the surface, those modes aren't propagating up through the solar photosphere. They're trapped, right? Remember that yellow ball that showed the modes being bounced back down. And that's because they sit below the photospheric acoustic cutoff frequency, which is a special frequency determined both by gravity and the sound speed. And if you're propagating with a higher frequency, those waves can propagate up. If you're propagating with a lower frequency, they're trapped, and they're essentially standing waves in the solar interior and photosphere. And essentially the reason is a lower frequency wave has a longer period. A longer period wave has a longer wavelength. And for those wavelengths, for waves propagating up, the wavelength is longer or of the same magnitude as the gravitational scale height of the atmosphere, right? In a gravitationally stratified atmosphere, the density is dropping off exponentially with a certain scale height. And when the wavelengths get long compared to that scale height, then it's not that simple wave problem anymore of just waves propagating in a uniform medium. It's waves propagating through a background medium that's changing a lot, and it's changing rapidly for these low frequency waves. And in those cases, you get wave reflection, wave refraction, essentially all different ways of modifying and trapping waves. And essentially the energy of these very, very low frequency waves are evanescent. They decay exponentially as you go up in height. So that's essentially trying to explain why the internal P modes are stopped at the photosphere and they don't just keep on going up into the corona. There's also the internal gravity modes, sort of qualitative cousins of if you have a buoy on the ocean and it's bobbing up and down, gravity is the restoring force for that as things propagate horizontally. And they can exist a little bit in the corona, but in general, you don't really see them too much. They're mainly living deep in the solar interior. They don't survive too much up to the surface. All right. Is that all? Well, unfortunately, no, because there's another type of flavor of wave modes that can exist in the corona. And that happens when, if you're following a specific bundle of magnetic field lines, like a coronal loop, and the properties inside the bundle are different than the properties outside the bundle. The densities and the magnetic field strengths can be different in those different regions. And when that's the case, then there's this sort of wall between the interior and the exterior. And that wall can oscillate and it can undergo these different types of fluctuations, right? There's this so-called sausage mode where the overall cross-section gets bigger and smaller, like a sausage. There's the kink mode that we talked about before, where it sort of looks like an Alfvén wave propagating back and forth, but it's still, this actual thing is confined to the interior of this flux tube that is defined by different properties at the walls. And then there's higher modes, the so-called fluting modes, they're essentially shape-changing modes where the cross-section can undergo all sorts of geometric changes as well. And we see these things. I mean, there are these transverse kink modes that are seen in the flux tubes in the intergranular lanes. They propagate up with speeds that are sort of like a weighted average of the inside and the outside speeds. So they sort of act like Alfvén modes, but it's a little bit, it's in between. And there's also different types of mode coupling, where specifically as you pass through the chromosphere, where the plasma beta crosses from much greater to 1 to much less than 1 up in the corona. But when it's around 1, then the sound waves and the Alfvén waves are propagating at the same speed, so they can couple with one another quite a bit. There are these simulations by Siraj Hassan where they took a magnetic flux, sticking up through the solar surface and being jostled back and forth. And as it's jostled back and forth, the surrounding plasma, it pushes against the surrounding plasma. And that plasma has inertia, so it sort of pushes back. And that pushback generates these pressure modes that can be excited both sideways outside the tube, but can also be ducted along the magnetic flux tube also. I wish I had a movie for that because it looks pretty cool when the thing is jostling back and forth. But yeah, there's all sorts of different things that can happen. So a question in the chat about what determines the density in the interior of the flux tube. Usually what it is a balance in the total pressure between the magnetic and gas pressure inside and the magnetic and gas pressure outside. So if it's a strong magnetic field inside the tube, then that means that the density on the inside can be lower, and then the density on the outside can be higher where the magnetic field is weaker. So that's one way it can happen, but I think I've seen examples where it's the other way, where it's a dense tube with a weaker magnetic field surrounded by a stronger, lower density medium. But yeah, all sorts of different things can happen in the corona. All right. I've already sort of talked about how some of these waves are generated at the surface of the sun, right? You can have these vertical flux tubes that are jostled back and forth. You can have some sort of convective-driven P-mode power that might survive as you go up to larger heights. There's the flares that can trigger waves that can propagate out. There's only one other generation mechanism I wanted to talk about because it's sort of a classic physics thing from the 1950s. That is this idea of of James Lighthill's theory of jet engine noise, which was developed to try to understand how loud jet engines can be. But really, it's a general theory for taking some compact but very incoherent source of energy. In the case of the sun, it's like convection. In the case of a jet engine, it's the actual engine itself. But then in the case of both of those things, if you look far away from them, some remnant of that incoherent energy gets turned into waves that propagate in the sort of far field limit. Maybe there's even a similarity to gravitational wave sources here too, where something complicated happens and then what's left propagates out as waves far away. And yeah, for acoustic sources like jet engine noise, the energy flux that comes out of it can be written in a pretty simple way. And it's kind of amazing that it's proportional to the velocity fluctuations in the source to the 8th power. So very small changes in the source can cause large changes in the waves that are far away from it. Yeah, I mean, I haven't seen this used too much by solar physicists, but stellar physicists who are trying to generalize models of coronal and chromospheric heating to other stars often use models like this to understand how things scale when you change the properties. And I tend to sometimes focus, maybe it's a subjective thing, but I sometimes focus on things that are directly back in my own academic genealogy. Lighthill was my great-great-great-grandfather advisor, I guess. Yeah, it's kind of fun to look back on things like that. Never got a chance to meet Lighthill, but I've met all the others in the chain there. Yeah, okay, that's the generation. I wanted to talk a little bit about how waves propagate up. There's a little more theory here to try to figure amplitudes evolve as a function of height as you go up into the corona. If you really want to look at this, it's sort of a similar kind of energy conservation equation as the ones we've been looking at before, where here the capital U energy density is the energy density being carried by the waves. There's a wave energy flux, and then there's, if this right-hand side was 0, then that means the waves are just propagating in an undamped way, but you can have a negative sink term on the right-hand side to show how the waves dissipate their energy and turn it into heat. But we can simplify it a little bit first. We can ignore the damping and the heating. We can ignore the time variations and just assume sort of a time steady source of waves that are propagating up. Then it's really just one term. It's the divergence of that energy flux being 0. I don't know how often you've seen a vector divergence being written in this sort of way with a generic area factor. As you're following the magnitude of the vector as you're going in one direction, that I'll call height or radius. That area factor really can be a whole bunch of different things, right? If you're in a Cartesian geometry, it's constant. If you're in a cylindrical geometry, it's increasing as the radial distance to the 1 power away from the axis. Spherical geometry, it's r squared. Or if you're just following some generic collection of magnetic flux tubes, the area goes as 1 over the magnitude of the magnetic field because the magnetic flux is conserved. But whatever the A is, if you know it, then the flux is going as 1 over that area. And how do we write the flux? There's all sorts of ways to do it for all different types of waves, but for the primary 2 main types, the sound waves and Alfvén waves, you can essentially just write it as the energy density, which is this, density times velocity amplitude squared factor, times the group velocity, how fast does the wave propagate energy through the system, which essentially is just either the sound speed or the Alfvén speed in these 2 cases. But we can put these things together and learn about how the waves change their amplitude as a function of height. For sound waves, we can, we can assume that the area factor is constant because we're just looking at waves that go sort of straight up for a little bit above the solar surface. We'll eventually see that they don't last that very long, so that's not too terrible an assumption. So we can set this flux equal to a constant, and then we can sort of rearrange things and solve for the velocity amplitude. It essentially goes as the density to the -1/2 power times the temperature to a power, but the temperature isn't varying all that rapidly from the photosphere to the chromosphere, but the density is dropping off by many orders of magnitude. We could do it a little better and fold in the model of the chromosphere from last week with a specific shape of this radiative cooling function. But all that does is give us a delta V that goes as density to the minus 0.4. But if you ignore it, it's just density to the minus 0.5. It's pretty close. But in general, what that means is that the wave amplitudes grow with increasing height as the background density is dropping. And eventually you're going to reach a point where the velocity amplitude grows to such a strength where it's as big as the sound speed itself. And this now becomes a very nonlinear wave, right? If that delta V parallel is small compared to the sound speed, and if you start off with a sinusoidal wave train, the whole thing essentially moves together. But if the delta V parallel is of the same order of magnitude as the sound speed, then the crests go faster than the average wave, the troughs go slower than the average wave, and the whole thing steepens into a set of sawtooth type shock waves. And this is a numerical simulation of what you get in one dimension if you drive the photosphere with sort of a piston, and eventually you see these strong shocks in the chromosphere. And so, yeah, there's some observational evidence for it, but of course the real sun isn't 1D, so this is a simplification. But yeah, there's a lot that happens to these waves as they grow. I wanted to switch gears and just mention the Alfvén waves because a similar thing happens with them. You can do things a little bit different. You can assume that this area factor goes as 1 over the magnetic field strength because Alfvén waves care a lot about the magnetic field lines. And you can play around with these flux going as 1 over the area type expressions. Turns out the magnetic field cancels on both sides because you have an Alfvén speed here. And it turns out, yes, the transverse amplitude of the Alfvén waves also increases with height. It goes as density to a minus power. And this density to the minus 1/4 power is precisely what we see in the left-hand part of this observational potpourri that I showed before. There's other stuff that happens out in the solar wind, but that's going beyond the simple analytic model that I just showed here. We'll talk a bit more about evolution of Alfvén waves in the solar wind in a few weeks. But yeah, I just wanted to show that, yeah, this is sort of what happens for undamped Alfvén waves. They increase, and we actually observe them not to increase as much as density to the minus 1/4, which means that there is some damping that we can see happening in the lower corona, and even more as you go out to the solar wind as well. All right. Yeah, that brings us to talking about dissipating the waves and turning that oscillation energy in those different amplitudes into randomized thermal energy for the particles, and that's heat. There's a lot of ways that waves can damp. I list 4 of them here. I'm really only going to talk about the first one right now, just because there's a lot to talk about. If anybody's curious about these other methods like shock dissipation, which ultimately might be related to collisions, which I'll talk about. There's also radiation and plasma physics, wave-particle interactions that can all sort of produce irreversible damping of a wave. Please let me know. We can talk about it in the Slack or offline or anything like that. But yeah, I can just sort of talk right now about particle-particle collisions as the canonical way of dissipating wave. And if you've never delved too deeply into particle-particle collisions, really what they do is they randomize the system, right? They're on very small scales. You've got particles moving around randomly. Occasionally they come close enough to one another to undergo sort of electrostatic attraction and repulsion. And if that's happening millions and millions of times, the particles sort of random walk their way through the system. And what they can do is transport things through the system by this very randomized a way of doing things. I guess there's, I guess in biology, when cells transport things across barriers, it's all happening by balancing different rates of random transport in different directions. And it's this diffusion across space and time that we're talking about here, right? If you have strong gradients in things like momentum or energy, and you pop on collisions, the collisions smear out those sharp gradients. So you get effects like viscosity from velocity shear. You get electrical resistivity when you have ions and electrons going in different directions, making currents, and other things. We talked about heat conductivity last time. Question in the chat about, isn't the corona collisionless? Well, down at the base, collisions are somewhat important because heat conduction, we've seen, has been dominating some of the coronal heating. But the higher up you go, collisions do become less important. Yeah, if you go all the way out to 1 astronomical unit in the solar wind, there's roughly 1 particle collision per astronomical unit. So there's, it's happening rarely. But they're still somewhat happening. And then there's all these other effects that can pop in, like these plasma physics effect. Yeah, there's various things that can happen in the corona as well. But yeah, there's a lot that can happen. I'm sort of picking on collisions here as a classical example, but there's other things that can behave sort of like collisions in different places too. All right, well, what these dissipation things do is produce sort of an imaginary term in the dispersion relation, which means essentially if you have a frequency or a period, there's an imaginary component of that. And what does that mean? Well, the amplitudes normally go as e to the I omega t, right, sinusoidally with the frequency. But if there's an imaginary piece, that means there's an exponential damping piece, which is what I really mean by damping and dissipation. The energy dissipation rate, which I showed as the minus Q damp on the right-hand side of the energy equation, can be written in terms of the this damping rate. Yeah, there's all sorts of interesting physics. There's a factor of 2 there because the energy is damping out. The energy is proportional to the square of the amplitudes, and if you square this, you get e to the minus 2 gamma. So it's a rate of 2 gamma. I've pulled out this plot from one of my papers from 10 years ago now that showed these damping rates for a model of the corona and the solar wind as a function of height for the various sources of collisional damping, conduction, viscosity, and resistivity or ohmic dissipation. It turns out that the compressive modes, the fast and the slow MHD modes, which are the dotted and the dashed curves here, have very high rates of damping. And if you convert the damping rate in time into a damping length by basically saying how fast does it travel divided by the damping rate, that tells you how far you go before it damps out appreciably. And for these acoustic type sound wave type modes, they don't last long. They only go about 10 to the minus 4 solar radii before they get very strongly damped for a typical period. On the other hand, the Alfvén waves, they don't feel this conductive damping, which is the strongest thing in the corona. They feel some other sources. Notice there's no blue solid curve here, which means there's no conductive damping for the Alfvén waves. And their damping length is many, many solar radii. So the Alfvén waves can very easily escape the corona and go out into the solar wind. So yeah, here this is just the visual summary of all that, right? If you have compressive waves like acoustic or sound waves, and they're generated at the sun, they don't usually last that long. They're mostly damped out by the coronal base, but there are probably other sources of compressive waves that are generated more gradually, like there can be these flares that generate power at the base of the corona. You can have some sort of mode conversion from the Alfvén waves to the compressive waves. It's still an active topic of research to figure out how the small amount of density fluctuations that we see are generated. But yeah, in general, the Alfvén waves that are generated at the surface have no trouble escaping all the way out. All right. I think that was my 40-minute summary of waves in the corona. I did want to talk about one more thing today, and that's turbulence. We'll continue talking about the more MHD versions of magnetized turbulence next time, because that actually relates to reconnection and nanoflares quite a bit. Here I'll just talk about the hydrodynamic turbulence of unmagnetized fluids. long history, of course. Leonardo da Vinci is the one who named it and really subjected it to scientific scrutiny, right? There's plenty of times when we see fluids that don't obey a nice sinusoidal oscillations. They're very chaotic and stochastic and random. And it wasn't until the 20th century that, the full sort of statistics, mathematical packages were applied to all this to try to understand what's really going on. And what is really going on in a lot of cases is, as I said before, it's not a transport of energy through space, but it's a transport of energy from one scale to another. And what happens in fluids is that you've got these nonlinear terms in the momentum equation, the Navier-Stokes equation, and they basically allow, if you have some sort of large structure of moving, gas or fluid, and you perturb it just a little bit, you put a little bit of a force, a little more of a force on one side than you put on the other side, it'll start to distort, and it'll distort a little more and a little more, and essentially it becomes shredded. It essentially gets disrupted, and all of that energy that used to exist on this large scale gets distributed to smaller and smaller and smaller random scales. That's one way to think about it. You start off by injecting the power at the largest scale by spinning this thing up. It doesn't always have to be a vortex like was in Da Vinci's drawings, but that's the classical example. And then you let it go, and the power, the actual energy, the kinetic energy, sort of drains out of this large scale and fills up the smaller and smaller scales. So I don't know if you've seen the poem. I think this was a spoof of something from Gulliver's Travels or something, of big whirls have little whirls which feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. And the viscosity is what happens at the very end of this process, because when you have tiny little things, that's what can trigger the Coulomb collisions to damp them out and cause heating. So yeah, in words, I just said this, but maybe a picture is worth 1,000 words, because if you plot all this as a Fourier power spectrum, that sort of tells the same sort of story. You're injecting the energy by stirring the system on a large scale or a small wave number, and there's this natural breakup into smaller and smaller eddies, which means that the power is sort of transported from the large scales to the small scales. But then there's a point at which viscosity or some collisional or collisionless damping happens, and the actual kinetic energy fluctuations go away. And where does it go? It goes into heat. So the cool thing about turbulence is that if everything is happening in a time steady way, then all these different rates actually balance each other, right? The rate, I'm using Q again for this rate of energy per unit volume per unit time. The energy that's going into the system by stirring it is the same rate as the energy that's cascading down from one scale to the next. The same energy that's leaving the system by damping, that's the same energy that's going into the particles as heating. So I guess the dirty little secret of turbulence is that if you have a turbulence model of coronal heating and you don't care too much about the details of what's happening at the smallest scales, you don't need to know the physics of how the heating actually happens. If everything is time steady and stationary, then all you need to know is the rate at which energy is going in, and or the rate at which energy is cascading down the pipe to the smaller scales. And that tells you the heating rate. And again, essentially, time steady means that the system sort of works out how to dissipate it and keep everything all time steady. There's a lot being swept under the rug there, of course, and solving the coronal heating problem really is going to involve all those different stages. But it's interesting to see how far you can get with just looking at these larger and cascade scales. So for example, you can work things out analytically. You can figure out, well, if you've got an eddy at a certain size and a certain velocity that's sort of going around at that size, we can sort of write down what I call the first postulate of strong turbulence, and that is the way that turbulence differs from waves. And that is that if you look at the time scale of the fluctuation, which is called the sort of the circulation time, or maybe the crossing time, basically the length divided by that velocity. The postulate says that that is the same as the lifetime of the eddy. Essentially, once you create it by stirring it, it only lasts as long as one oscillation time, right? That's very different from waves because the lifetime of a train of waves goes for much longer than one period. But here we're saying the lifetime is essentially one period for a turbulent eddy. But if that's the case, then that lets us write down the cascade rate. The cascade rate is basically how long does it take to take the energy density of the eddy, which we sort of know how to write from waves, and how long does it take for that to be essentially destroyed and given to the next smaller scale to continue to go down the pipe. And that delta t is really this lifetime, right? Which you can write as the length divided by the velocity. So this turbulent heating rate, essentially the cascade rate, which is also the heating rate of density times the velocity cubed divided by the length scale at which you're stirring the system, is a surprisingly robust way of estimating coronal heating. You can do more, right? You can have a second postulate of strong turbulence that says that this rate is constant as a function of the wave number going down that inertial power law, and that eventually can be used to figure out what that power law index is, the -5/3 that we've now seen in the solar wind, pretty much. I won't go through that derivation, but what I can do is take this heating rate and write it in the notation of the Poynting flux times an efficiency that we looked at a couple weeks ago. And you can figure out, well, if it's written this way, then the efficiency has to scale in a certain way. I'll let you look at the details. And this essentially gives you the m and n exponents for hydrodynamic turbulent heating. And yeah, I think that is where I wanted to actually end it today, because going into a magnet, if you add a magnetic field to the system, you get MHD turbulence. And I just wanted to show you a preview of a very high resolution numerical simulation that shows how that works. There are eddies, there are whirls, but there's a lot of other stuff going on there too. There's also magnetic reconnection and all sorts of evolution of the magnetic field that I'm not even sure is shown in this kind of plot. But yeah, there's a lot more to it, and we will get there next week. So I guess the only thing I wanted to say, there's no reading assignment for next week, is because the hands-on exercise was a 2-week thing that's going to be sort of due next week. So yeah, please keep on thinking about that. As I said before, there's the Slack channel for a discussion about that. Or always let me know if you've got questions. But yeah, I guess that's where I ended up for today. And in the chat, we've had some other questions about, yeah, Gilly has posted some things about freezing in and collisions in the corona. Please feel free to follow up any of those links. Yeah, I guess that was it. Yeah, any questions about all this stuff? I threw a lot at you, but hopefully, again, these videos can be resources that we can go back to again and again, and hopefully they can be useful. All right, well, if that's it, I can stop the recording.